Alright, so section 2.7 deals with the precise definition of limits. So I'm going to walk you through one of the homework examples to go through this. So one of the homework questions is, suppose the absolute value of f of x minus 6 is less than 0.1 whenever x is between 0 and 6, and we're asked to find all the values of delta such that the absolute value of f of x minus 6 is less than 0.1 whenever 0 is less than x, the absolute value of x minus 2 less than delta. Okay, so this is probably your first exposure to the idea of epsilons and deltas. So let me start out with this one by drawing a picture. So I'm going to go to the next page here, and we're going to draw a picture. Okay, so first off, we'll start with the condition that we were given. We were told that whenever x is between 0 and 6, and let me put some tick marks here. Whenever x is between this range here, I'll mark it in red, the graph of our function has to be within 0.1 of the value 6. So let me mark 6 on here. And I'll also mark 6.1 and 5.9. Basically, above 6, this would be 6 plus epsilon. And then below 6, this would be 6 minus epsilon. And so we're guaranteed to stay within 0.1 of the value 6, of the y value 6, whenever x is between 0 and 6. So if I were to draw a sample graph, let me put 6 in here. I'm going to draw my function f of x in green. Anytime we're between the x values 0 and 6, we know that our f of x has to be kind of inside of this epsilon tube, if you want to think of it that way. Okay, we have no idea what is occurring outside of x equal to 6, so we don't know what's happening when x is greater than 6. We don't know what's happening when x is less than 0. All we know is that when x is between 0 and 6, we're guaranteed that the graph of f of x is going to fall somewhere between the values of 5.9 and 6.1. Okay? So again, I know that because my original expression, or my original hypothesis, tells me so. It says whenever 0 is less than x is less than 6, when that occurs, this happens. Our function minus 6, the absolute value of that is less than 0.1. That means it's within 0.1 of 6. Okay, so now we want to find all the values of delta such that we're guaranteed this still occurs. Okay, so this condition hasn't changed. We want this still to occur, but now we are changing up, the x interval that we're looking at. So let me go back to my graph. Okay, so if we're kind of centering ourselves around 2 now. Okay, so now we're saying we're kind of restricting ourselves to 0 less than the absolute value of x minus 2 less than delta. So we're looking kind of in the neighborhood of 2. So I know that I'm guaranteed for any x value between 0 and 2, I'm guaranteed to stay within the safe bounds of 0.1 away from 6. So I'm going to call, from 0 to 2, I'm going to call that delta 1. Okay, and that has a magnitude of 2. And we also know that if we are anywhere in the x values between 2 and 6, we're also safe, right? That was our original assumption. So I'm going to say delta 2 is equal to 4. So in other words, I can go from 2 to 6, which is a distance of 4, and still be safe. Okay, whenever you are trying to guarantee that you maintain the proper, or maintain your proper epsilon bound, when you have a scenario that you have two different deltas, you typically choose the smaller one. And the reason behind that is if we were to choose delta equal to 4, okay, the larger delta value, that would imply, via this statement, that x could be anything ranging from 4 to the right, so 2 to 6, from the number 2, or 4 to the left of the value of x equal to 2. We don't know anything at all about what the graph is doing from -2 to 0. So therefore the answer to this is delta is equal to 2. And that is the answer there. Okay, so, play around with this. This is really approaching some higher math. So we're just kind of exposing you to it. Draw some pictures. Hopefully it'll start to sink in a bit. Okay, let me know if you have questions.